Chun. This is my first, well, actually my second attempt at making a little tutorial video about dimensional analysis for you. My first attempt, my mic was turned off, so that was unsuccessful. Anywho, this is a part of your day 6 homework, and I'm going to dive into a new topic that's actually going to further connect what we've been talking about regarding measurement and also significant figures. This is a skill that we're going to continue to use throughout the year, so hopefully we're able to start off with a strong foundation today with just a few examples that may seem simple at first, but I want you to be patient and pay attention to the process of how I set things up, because that's going to be the most important part moving forward. Okay, so here we go. To kind of set the stage for what dimensional analysis allows us to do, it's basically a way for us to convert units from one unit into another. So why do we do this in science? Sometimes we collect data in terms of one set of units, and another group collects data in terms of another set of units. And to directly compare our results, right, one group needs to convert their data into the units of the other group. Another reason may be in chemistry we deal with some pretty extreme scales, so a lot of times we have to try to extrapolate or predict on a small scale what an experiment might look like on a large scale, in which case we'd have to convert our units. But anywho, I diverge. The point of this brief description is to show you some example calculations and ways to apply this method of dimensional analysis. So as you can see below, there's a calculation that involves multiplication and division, and it's centered around this example of how would we figure out how many days there are in 2.0 years. So if you can see some features of this calculation, we write out the initial measurement, right? And through sort of this multiplication problem where we express these two other values as a fraction, this 365 days and 1 year, we express that as a fraction. And some of you may have picked up already that, 365 days is equivalent to 1 year, right? So we're actually taking advantage of this idea of an equivalence factor. And in math, right, if your numerator is equivalent to your denominator, you're essentially dealing with a value of 1. And any number multiplied by 1 will preserve its value, right? So that's kind of the big picture idea behind dimensional analysis. So without further ado, I'm going to move forward to the next slide and talk a little bit more about what I mean by this equivalence factor or this conversion factor, okay? In dimensional analysis, we're going to express this conversion factor as a fraction. There's going to be a top number and a bottom number, and we're going to say that both of those values are going to be equivalent but expressed with different units. So in this case, the 365 days being equal to 1 year, that's what makes this second part of the calculation our conversion factor. Okay, and the purpose of a conversion factor is to basically help us convert a number with one set of units into a different set of units. So in this case, the conversion factor of 365 days to 1 year helped us to convert 2 years into 730 days, okay? Moving forward though, I want us to actually go through an example together. And this example is a little bit more relevant to what we might come across in our chemistry class. So I'm gonna actually switch tabs. For whatever reason, my little digital writing tool helps me, allows me to write better in Google Draw, but anywho. In this example, we had taken the mass of a metal and found it to be 2.35 grams, but we're going to need it to be in terms of kilograms for the answer to this problem. So I went ahead and I gave you a conversion factor. So this right here, this statement, the 1,000 grams is equal to 1 kilogram. That's what we can call our conversion factor, okay? Conversion factor. And so the general process, wow, whoa, sorry, oh my gosh, my pen is really running away from me. Let me delete that a little bit. Sorry, got a little lost there. Conversion factor. There we go. Okay, we're gonna start off with the value that we're initially given. So this 2.35 grams represents the initial measurement, right, that we are trying to convert. So you're always going to want to start off your dimensional analysis calculations with what you're given, what your initial measurement is, okay? And in chemistry class, it's really important that you don't just write the number down, but you also attach units to it, okay? And our goal is to figure out how many kilograms this number is equivalent to. So here's where we take advantage of the conversion factor. We're going to multiply the 2.35 grams by a fraction. Now, how do you know which number goes on top and which number goes on bottom? Well, in math class, you may have learned that whenever you're multiplying a series of values, if there's a value that appears on both the top and the bottom of a fraction, you can cancel those values out. So we're going to take advantage of that rule. And whatever unit is in your initial measurement, that's the unit that's going to immediately go diagonally on the bottom of the fraction here. Okay, so grams and grams, you see that? And we're trying to convert grams to kilograms. And what's convenient is this conversion factor allows us to make a one-step conversion, right? We can go directly from grams to kilograms. So that's going to go on the top here. Okay, and then we can fill in the corresponding numbers from the conversion factor. So we see there's 1,000 right next to the grams, and that's equivalent to 1 kilogram. Okay, and now I'm in the home stretch of my calculation. I take the 2.35, I multiply it by 1, which gives me 2.35, and then I divide it by 1,000. You can either do that in your calculator, or you may know the trick that if you divide by 1,000, you bump the decimal to the left 3 times, which would give you a final answer of 0.00235 kilograms. Okay, I'm going to label and circle my final answer, and there we go. Even if some of you were like, wow, Ms. Chen, I could have done that in my head. I'm just going to do mental math from now on. Please don't do mental math from now on. I need you to write out your calculations, even if they seem simple at this point. I promise you, as we build on the content, you're not just going to be dealing with one-step calculations, or maybe even 2 or 3-step calculations. You may be dealing with 4-step, 5-step, 10-step calculations, in which case it takes the mental load off to write out your work, and it helps to make sure you don't make a mistake along the way. So please do this moving forward. I wanted to mention one more thing. Some of you may be thinking, but wait, we just learned about sig figs. You have to make sure that there's the correct amount of sig figs in your answer. You're absolutely right. Here's the good news about conversion factors. In this case, right, if you were looking at the numbers 1 and 1,000, you would say immediately like, oh, those only have 1 sig fig in their numbers. We should probably round this number to 1 sig fig. If you were just looking at the general rules of sig figs, you'd be right. But in this case, we ignore the amount of sig figs in a conversion factor because conversion factors do not affect the accuracy in our initial measurement. So therefore, when you're dealing with dimensional analysis and you're trying to apply rules of sig figs, you only care about the number of sig figs in your initial measurement. You ignore the sig figs of your conversion factor, okay? So 2, 3, and 5 are all significant figures in 2.35. So we only need 3 sig figs, SF sig figs, in our final answer as well, which we do, right? We have 2.00235, so we have 3 sig figs in our final answer, so that checks out, okay? We don't care about the sig figs in our conversion factor. And I'm going to re-emphasize that on this next slide by going back to our original example, okay? Remember, our original example involved converting 2 years into days. And in this example, if you just looked at these numbers, you'd say, hey, 365 has 3 sig figs and 1 has 1 sig fig. Shouldn't we round this to 1 sig fig? My answer would be no. We ignore the number of sig figs in the conversion factor, and we only pay attention to the number of sig figs in our given initial measurement. So 2.0 has 2 sig figs, which is why it's correct to report our final answer with 2 sig figs. Okay, that's just an FYI, so hopefully that detail sticks with you as we move on. But that concludes my little discussion about dimensional analysis, and it's going to be up to you to fill in what I just talked about onto slide 6 and to apply it to slide 7. So a few notes about slide 7 in your day 6 homework. I need you to show me your calculations for each of these conversion problems. The conversion factors can be found at the bottom of the page, and I want you to use the method of dimensional analysis where you show me the conversion factors using the fraction form, okay? Please show me all your work and insert a picture of your handwritten work in the space below. Okay, thank you for listening. and good luck.